So what we're looking at here is a review of what we did last time. We started looking at conservation of momentum. When we look at conservation of momentum, what we found here is that if we had a system that was in dynamic equilibrium, that meant that it had zero acceleration, that its center of mass had zero acceleration, and as a consequence, V center of mass was a constant. Directly from that, or an equivalent statement, is that conservation of linear momentum is an equivalent statement of saying that the system is in dynamic equilibrium. But we don't talk about the velocity center of mass, we talk about the total momentum of the system. That means that the total momentum of the system before and after a collision is the same. In other words, the system has to readjust its momentums after a collision to keep P total constant. So the way we started looking at this is that we looked at elastic collisions. So when we looked at elastic collisions, we said that they were perfect collisions, that there's no heat generated or sound generated or light generated. There's nothing. All of the motion all of the momentum stays with the motion here, as well as the energy. And what we ended up doing here is that we broke it up into 3 cases, but we only got to 2 of them. So what we said here is that we looked at case 1. We looked at the situation of equal masses. So I have block 1 coming in at P1 initial, which is the red. And that's what we call the projectile. And then we had block 2, which is the target, had its momentum, P2 initial, equal to 0. So when I look at this as a system before the collision, and then I ask the question, are there any other forces other than the forces within the system? And the answer is no. There's nobody hitting the blocks. There's no friction. There's none of that. So what we then say here is that the external impulse of the system, or the net force, is 0. Therefore, the total momentum of the system must be a constant. And so what we said here is that the momentums have to exchange. So if you looked at the initial momentum of block 2, of a block, so the initial momentum of block 2 is 0. So you're seeing here is that this momentum gets transferred to the momentum in its final state. And then what we saw here is that the momentum P1 initial got transferred to P2 final. And this is a big story for conservation of momentum. Not only does it pay attention to magnitude, it also pays attention to direction. So if I look at a momentum bar diagram, here's what I'm seeing here. I see here that the momentum of P1 is going to the right. It has direction. Therefore, the momentum after the collision has to be the same height going to the right. And this is special only in the case of equal masses. And so that bar diagram essentially tells us then that P1 initial plus P2 initial must be P1 final plus P2 final. And in this situation, we're seeing here is that this guy is 0. This one is 0. So then these two momentums are equal and opposite here. Then we went to our second case where we dealt with a massive target. And I think this is a really hard one. Here's where momentum gets really, really tricky in everyday language. So what we're shooting here is that we're shooting a golf ball or throwing a golf ball at a bowling ball. And what do we find out here? Well, physically, what we would expect that the golf ball is going to come back with roughly the same initial speed. Roughly. And if you've ever thrown a golf ball at something really massive, you want to pay attention because that thing's coming back pretty damn fast. So now what we would expect here is that the bowling ball is going to barely move on to the right here.
I'm telling you, people that do notes.
Yeah. You have a question? Okay.
Did I raise my hand?
No, you're on.
Did you have a question?
No, I'm sorry.
Okay. Make sure you mute yourself. Okay. So then what we want to do here is that when we're looking at this, what we want to pay attention to here is that we want to be able to suspect here that the bowling ball is going to be moving very slowly off to the right here. But without a bar momentum diagram, it's pretty hard to kind of intuitively understand what we said here. And what we said here is that I am trying to say right here that the momentum of these two are going to be roughly the same. And this is something that we should check mathematically in our example. And so then what does the bowling ball do to the golf ball? Well, the first thing that it has to do is it has to stop the initial speed of the golf ball. And then it has to speed up the golf ball to go to the left now. So what you're seeing here is that the momentum transfer to the golf ball is much larger than the actual initial momentum. And the reason why it has to be that way is that the golf ball going in the negative direction actually reduces the overall momentum of the system because of that. So even though the golf ball is moving very slow and its momentum is quite large, the reason why it's so big here is because its mass is big. So we would expect then that this would be larger than the golf ball that came in at some high initial speed. So there's more momentum of the bowling ball going out than what came in. But remember, we got to be careful because we have to account for the negative part. So now let's go to the last piece before we move on here and look at it an example. We want to look at a massive projectile. So if I look at a massive projectile, what is it that I'm seeing here? So remember, I want to set up the same thing. I need a before and after, and I need to identify my system. So in this situation, what we imagine here is that we're taking a big block, a bowling ball. And what we're going to do here is that we're going to throw it with some momentum going inwards like this. And then what we have here is we have a stationary target, which is at rest. So when I'm looking at my picture here, and I look at my system again, my system tells me, are there any other forces besides the collision forces? So again, this is the analogy of this being a bowling ball being thrown at a golf ball. So we expect that the bowling ball's not going to lose that much speed, right? We would expect that after the collision, that the bowling ball's momentums should be initially equal to what it is afterwards, effectively. Of course, it can't be completely, the same here because it has to give up some momentum to transfer to the golf ball. So then we would expect that the golf ball to now be moving off with some momentum that's moving to the right in that direction now. So there's a couple of things that we want to ask here. And the question is this: do we know anything about the speed of the golf ball? Not really. But there's ways that we can look at it to get a sense of it. But what does the bar diagram actually tell us before we move on? So when I look at the bar diagram, it's telling me I have this amount of momentum. And where is that momentum going? It's going to the right. The momentum of the golf ball, of course, initially is 0. So what this tells us here is that these momentums have to adjust to keep this guy constant. The total momentum of the system must remain constant. But we can use intuition. We would expect that most of the momentum is going to stay with the bowling ball. But it has to give some up to the golf ball. And we expect that that golf ball is going to get a little bit of that momentum. So when I'm looking at this thing, this is the picture that I'm actually seeing here. So the question that we're really asking, what does this tiny momentum tell us about its speed? Okay. Well, there's a couple of ways to look at this thing. And probably the best way to look at this thing is to jump into a different frame of reference. So now what we want to do here is that we want to jump into another frame of reference to understand the speed of the target. So what do I see here? Well, I imagine that I have my bowling ball coming in, right? So I have my bowling ball coming in. And if this is truly a bowling ball, then what I'm seeing here, I'm going to see that the momentum of this bowling ball is not going to change much when it collides with this guy right here. So when we're looking at this frame, then what this is telling me is that I want an observer right here on the ground, right? So here's my observer. And if my observer's on the ground, what he states here, she states that the bowling ball does not change speed by much. Right? And intuitively, that's what we would expect here. Are you guys still here? Am I
Yes.
still recording?
Yes.
God, man. It's telling me that
Yes, we're still here.
no. But Zoom is telling me that it's about to close down because nobody's here. That's why I'm saying that. Yeah. I'm
What
gonna
was
hope
it?
that it does
You
not.
had an extra class open when we first joined, and we had to enter the Zoom ID again.
Okay. Okay. Okay, then I'm gonna ignore that then. So now let's check this out here. Now what we want to do here is that we want to change frame of reference. So the way I want to change my frame of reference is that I want to do this here. I want to come in here and I want to look at this block. And what I'm going to do is that on this block, I'm going to jump onto block 1. So now here's my observer. Now note, as far as this, if this block 1, this guy now sees that the observer sees the block 1 at rest all the time. So what actually happens here is that if this guy's moving with some speed and it's moving it, so if this guy is moving at some initial speed, this guy is now going to come in with a momentum that has a speed here of 1 initial like that. Okay, it's going to come in at that value. So when I'm looking at this guy, this is what I see beforehand. But then, so should not be a surprise. Why should this not be a surprise here? Because now, look at this. I have a small projectile and a big target. But didn't we just study this right here? We sure did. We just looked at this guy. So what do we expect the projectile in this case to do? It's going to bounce off. And it's going to roughly bounce off at the same speed. So what then we see here is that then afterwards, the momentum of the block, it is true that it's going to be moving in this direction. But now look at the speed at which the target moves off. It should move off with the speed of roughly true final equal minus V initial. So now, you know what? I should be really careful. Let me put in some signs here. Let's make this the negative sign in that direction, and let's make this the positive sign. So then that means here that this guy should then be a positive because that's the velocity that's moving in that direction. So what I'm seeing here is that block 2 changes speed by, so if I look at block 2, I have a negative speed and I have a positive speed. So this is going to be V2 final minus V2 initial. But if I put this into this language, this is then going to be positive V1 initial minus V1 initial. So it should be coming out at twice the speed of the projectile's speed. So even though this has a tiny, tiny momentum, that golf ball comes out twice as fast. That's a big deal. So this tells us here is that the golf ball, after the collision, roughly leaves with twice the speed of the bowling ball.